Number 1. Isotope bromine 79 has an atomic mass of 78.9183 AMU, or atomic mass unit, and we're given the relative percent abundance for that isotope. Now we're also given the same information for isotope bromine 81. We have the atomic mass and the percent abundance. So with this information, how can we calculate the average atomic mass of the element bromine? So there's a formula that we could use. It's equal to the mass of the first isotope times its percentage as a decimal, plus the mass of the second isotope times its percentage. Now, if you have 3 isotopes, this can continue, or if you have 4, so it would be plus M3P3 plus M4P4. But we only have 2, so we can stop here. In this case, M1 is the mass of the first isotope, so that's going to be 78.9183. P1 is the percentage for that isotope. Now we need to convert it to a decimal number, and so we got to divide 50.69 by 100. So that's going to be 0.5069. Now the second mass is 80.9163, and now we need to multiply it by its percentage, which is 0.4931. So you can also move the decimal point 2 units to the left if you're dividing that number by 100. Now, let's plug these numbers into a calculator, and let's get the answer. So what I got is 79.90. And so this is the average atomic mass of the element bromine. And you could check this answer out. You can go to Google Images, look up the average atomic mass for bromine using a periodic table, and you should get about 79.9. And so that's how you can confirm your answer in this case. So that's it for this problem. Now you know how to calculate the average atomic mass of an element. Now let's move on to our second example. The average atomic mass of boron is 10.81 atomic mass units based on the stable isotopes B10 and B11. And we're given the mass of each of those stable isotopes. Part A. Calculate the relative percent abundance of each isotope. So in the last problem, we had the percent abundance of bromine 79 and bromine 81. It was about 50.69% and 49.31% respectively. In this problem, we need to calculate those relative percent abundances. So basically, we're working in reverse. Now we're going to use the same formula where the average atomic mass is equal to M1P1 plus M2P2, since we still have 2 isotopes we're dealing with. If you go to the periodic table, you should see this for boron. It has an atomic number of 5 and an average atomic mass of 10.81. Now it's important to understand that when you see this number, it represents not the mass of an individual isotope of boron, but rather the average mass of all the isotopes of boron on the Earth. So just keep that in mind. On the left side, we're going to plug in the average atomic mass, which is 10.81. The mass of the first isotope, we're going to say that M1 corresponds to B10 and M2P2 corresponds to B11. So the mass of the B10 isotope is given to us as 10.0129 times its percentage. Now, the percentage we don't know, so we're looking for that. Let's call it X. Now the mass of the second isotope, B11, is 11.0093. Now what should be the percentage of the second isotope? Let's think about this. Let's assume that 30% of the boron atoms are B10. If there's only 2 stable boron isotopes, that means that the other 70% has to be B11, because these two have to add up to 100. Now, we need to deal with decimal numbers and not percentage-based numbers. So 30% is basically 0.3. 70% is 0.7. So if 0.3 is x, we could say that 1 minus x is 0.7, because 1 minus 0.3 will give us 0.7. And that's what you need to understand when dealing with this problem. So if P1 is x, P2 has to be 1 minus x. Now, it's time to do the math. So on the right side, we have 10.0129x, and we need to distribute this number to 1 and negative x. So it's going to be 11.0093 and then minus 11.0093 times x. So let's go ahead and combine like terms. So 10.0129 minus 11.0093, that's going to give us negative 0.9964x. Now our next step is to subtract both sides by 11.0093. So on the right side, this is going to disappear. So this is going to be, let's see, 10.81 minus that number is negative 0.1993, and so that's equal to negative 0.9964x. So let's get rid of some stuff here. I'm just going to rewrite what I have above. Now what we need to do at this point is divide both sides by negative 0.9964. And so this will give us the value of x. Which is 0.2. So P1 was associated with x, and P2 was associated with 1 minus x. Now, if x is 0.20, that means that 1 minus x, which is 1 minus 0.20, that's 0.80. So this tells us that 20% of all of the boron atoms is the B10 isotope, and 80% of all of the boron atoms consist of the B11 isotope. Now, does that answer make sense? Notice that the average is 10.81. The average atomic mass is closer to the mass of the heavier isotope. The reason for that is because we have more of B11 and less of B10. So because B11 is more abundant, the average atomic mass is closer to the mass of the B11 isotope. Now let's move on to part B. In a sample of 600 boron atoms, how many B10 atoms are there? Well, let's find out. So we know that 20% of the boron atoms will be the B10 isotope. So we got to multiply this by 20%. So this is the same as 600 times 0.2. And 600 times 0.2 is 120. So in a sample of 600 boron atoms, 120 out of those 600 boron atoms will be the B10 isotope. In the case of B11, it's 600 times 0.8. And that's going to be 480 B11 atoms. And as you can see, the total adds up to 600. So if you had a sample of, let's say, 1,000 boron atoms, 800 will be B11, and 200 of those 1,000 would be the B10 isotope. Now let's move on to the next problem. Calculate the molar mass of each of the following substances. Well, first we need to know exactly what the molar mass means. What is molar mass? The molar mass of a substance is the mass in grams of 1 mole of the compound. So let me give you an example. Let's analyze carbon. Carbon has an atomic mass of 12.01. And so what this means is that carbon has a molar mass of 12.01 grams per mole. That's how you could find the molar mass using the periodic table. So if we had 1 mole of carbon, we would have a mass of 12.01 grams. Now you might be wondering, what is a mole? A mole represents a quantity of something. For instance, when you hear the word dozen, what do you think of? A dozen is 12. So if you have a dozen pens, you have 12 pens. If you have a dozen eggs, you have 12 eggs. Well, a mole is like a dozen. It represents a number, a quantity. A mole is 6.022 times 10 to the 23. In this case, 1 mole of carbon atoms is equal to 12.01 grams of carbon. And so the molar mass gives us a conversion factor. It tells us the connection between the quantity of carbon atoms and the mass of carbon. So here is what you need to take from this. When you're looking for the molar mass of a substance, you need to find the atomic mass of the elements involved. And the units will be grams per mole, or you can express it in terms of atomic mass units. But I'm going to use grams per mole. But you're going to find it based on the periodic table, looking at the larger of the two numbers here. So let's work on part A. What is the molar mass of potassium fluoride? So we need to add up the atomic mass of potassium and the atomic mass of fluorine. So you need to get a periodic table and look up the numbers using that table. So the atomic mass of potassium is 39.1 and the atomic mass of fluorine is about 19. So if we add these two numbers, 39.1 plus 19, that's going to give us 58.1. And the units will be grams per mole. So that's how we could find the molar mass of a substance. So what this means is that 1 mole of potassium fluoride has a mass of 58.1 grams. So make sure you understand what is meant by the molar mass. It tells us the mass of the substance if we have 1 mole of that substance. Now let's move on to part B. So let's calculate the molar mass of sodium carbonate. So what we have is 2 sodium atoms, or in this case ions because it is an ionic compound. We have a carbon atom and 3 oxygen atoms. So the atomic mass for sodium is 22.99. And for carbon, it's 12.01 based on the periodic table. And for oxygen is 16. So all we need to do is basically just add these numbers up. So go ahead and type this into your scientific device. So you should get 105.99 grams per mole. And so that's the molar mass of sodium carbonate. So 1 mole of Na2CO3 has a mass of 105.99 grams. Now let's move on to part C. So what is the molar mass of aluminum sulfate? So I'm just going to rewrite the chemical formula so you can see it more clearly. In this formula, we have 2 aluminum atoms. We have 3 sulfur atoms. There is an invisible 1 here if you don't see it. So if it's not there, it's assumed to be 1. So it's basically 1 times this subscript of 3, and that gives us 3 sulfur atoms. Now, how many oxygen atoms do we have in this compound? So in this case, it's going to be 4 times 3 because we have 3 sulfate units, and each sulfate carries 4 oxygen atoms. So we have a total of 12 oxygen atoms. Now the atomic mass for aluminum is 26.98. and the atomic mass of sulfur is 32.06. And for oxygen, we know it's 16. So let's go ahead and plug these numbers in and see what answer we get. So I got 342.14 grams per mole. So that's the molar mass of aluminum sulfate. Now let's move on to the next problem. How many moles are in 72 grams of methane? In order to do these problems and those that are coming up next, you need to become proficient at converting units. And for those of you who might need help in this regard, I have another video entitled Converting Units with Conversion Factors. And I'm going to post a link in the description section of this video so you can find it there if you don't want to search it on YouTube. But I recommend watching that video so you can get good at converting units, because every other problem that's going to come after this one, we're going to do a lot of unit conversion. So make sure you understand that topic before moving forward. So let's work on part A. How many moles are in 72 grams of methane? So what we need to do is we need to convert grams to moles. And the only way we can do that is by using the molar mass. So that's the first thing we need to do. We need to find the molar mass of methane. So methane contains 1 carbon atom and 4 hydrogen atoms. Now the atomic mass of carbon is 12.01, and for hydrogen it's 1.008. So let's go ahead and plug these numbers in. So you should get a molar mass of 16.042 grams per mole. Now what we need to do is take this information and convert it into a conversion factor. So what this means is that 1 mole of methane has a mass of 16.042 grams. So this is our conversion factor. So now what we are going to do is we're going to start with the information that we're given, and that is 72 grams of methane. And we're going to use our conversion factor to convert it from grams to moles. So the conversion factor will be placed in the second fraction. So because we have grams on the top left, we need to make sure that grams of methane will be on the bottom right, so that those units will cancel. And if grams is on the bottom, then moles of methane must go on the top. Now the number that's in front of the moles of methane is a 1, and the number in front of the grams is 16.042. So that's the way we need to set it up. Now we need to divide because we have a number on top and a number on the bottom. If we had 2 numbers on top, then we would multiply. So to get the answer, it's going to be 72 divided by 16.042. And so it's 4.488 moles of methane. So that's how you can convert from grams to moles. Part B. How many grams are present in a sample of 2.5 moles of NO2? So this time we're going backwards. We need to convert from moles to grams. So let's start with what we're given, 2.5 moles of NO2. Now just like before, in the next fraction we need to put the conversion factor. So in order to convert from moles to grams, we need the molar mass of NO2. And so we have 1 nitrogen atom and 2 oxygen atoms. So the atomic mass for N is 14.01 and for oxygen is 16. So 2 times 16, that's 32, plus 14.01. That's going to give us a molar mass of 46.01 grams per mole. So from this, let's write our conversion factor. and that is that 1 mole of nitrogen dioxide contains 46.01 grams of NO2. So this right here is our conversion factor. Now, how should we take this information and how should we place it in this fraction? So looking at the unit on the top left, we have moles of NO2. So we need to make sure that it's on the bottom right. And so on the top, we're going to put grams of NO2. Now the number that's associated with moles is 1, and the number associated with the grams is 46.01. So this time, because we have two numbers that are both on top of the fractions, we need to multiply those two numbers. So it's going to be 2.5 times 46.01. And so the answer is 115.025 grams of NO2. And so that's how you can convert moles to grams. That's how you can set up the conversion process. And make sure that these units cancel. Now let's move on to part C. How many atoms of carbon are present in 7.2 moles of carbon? So in this problem, we need to convert from moles to atoms. If you want to go from moles to atoms or atoms to moles, here's what you need to know. We talked about this earlier. 1 mole of something, it could be atoms, molecules, pens, books, doesn't matter. 1 mole of something is equal to 6.022 times 10 to the 23, which you know it as Avogadro's number. And so this is the conversion that we're going to use to go from moles to atoms. So, as always, let's start with what we're given, and that is 7.2 moles of carbon. Now, what should we write in the next fraction? Since we have moles of carbon on the top left, we're going to put that on the bottom right. So 1 mole of carbon is going to equal 6.022 times 10 to the 23 atoms of carbon. And so make sure you set it up in such a way that the units, moles of carbon, cancel. So what we need to do in this case is we need to multiply 7.2 by Avogadro's number. And so you should get 4.3358 times 10 to the 24 atoms of carbon. And so that's how you can convert from moles to atoms, by using Avogadro's number. Now let's move on to the last part of this question. How many moles are in 4.6 times 10 to the 23 atoms of nickel? So let's start with the information that we're given. Let me write atoms of nickel. When you're converting, there's 3 things that you need. You need the number, you need the unit, it could be grams, moles, atoms, molecules, and you need the substance. Right now, in the problems that we're dealing with, we're only changing the unit. Of course, we get a different number, of course, but we haven't changed the substance yet. In other problems, that's going to be something you need to be aware of. So not only do you need to convert the unit, you may need to convert from one substance to another. So just keep that in mind. So once again, we're going to use the same conversion. 1 mole is equal to 6.022 times 10 to the 23. So this time, I need the unit atoms on the bottom. So I can say that there's 6.022 times 10 to the 23 atoms of nickel for every 1 mole of nickel, because what's on the top must equal what's on the bottom in the conversion fraction. So these units will cancel, and now we're going to get what's left over, the unit on the top, that is moles of nickel. So this time, because we have a number on the top and one on the bottom, we need to divide instead of multiplying. So it's 4.6 times 10 to the 23 divided by 6.022 times 10 to the 23. And so you should get 0.7639, if you round it, moles of nickel. And so that's it for this problem. Now let's consider number 5. How many atoms of iron are in a sample of 235 grams of Fe? So in this problem, we need to convert from grams to atoms, but we can't do so directly. What we need to do is convert from grams to moles. We know how to do that using the molar mass. And then once we have the number of moles, we could use Avogadro's number to convert to atoms. So this is a multi-step process. Now the first thing we need to do is look up the molar mass of Fe. So using the periodic table, you should get 55.85 grams per mole. So what this tells us is that 1 mole of Fe is equal to 55.85 grams of Fe. So this is our first conversion factor that we need to use. The second one is just Avogadro's number. We know that 1 mole of Fe contains 6.022 times 10 to the 23 atoms of Fe. So let's begin. Always start with what you're given. In this case, 235 grams of Fe. Now, let's use the first conversion factor to convert it from grams to moles. So we need to put grams on the bottom. 1 mole of Fe has a mass of 55.85 grams of Fe. So we could cancel the unit grams of Fe. Now the next thing that we need to do is use the last conversion factor. We need to convert from moles to atoms. So since we have moles on the top, let's put it on the bottom. So 1 mole of Fe contains 6.022 times 10 to the 23 atoms of Fe. So now, let's perform the calculation. So what we're going to do first is we're going to take 235 and divide it by 55.85. Go ahead and type that in. So you should get, at this point, 4.2077. And then take that result and multiply it by this number. So the final answer that I got is 2.53 times 10 to the 24 atoms of Fe. And so that's it for this problem. That's how you can convert from grams to atoms without changing the substance. Now, if you look at part B, the substance is going to change. Part A and part B are similar because we're given the grams of this substance. That could be glucose or fructose, C6H12O6, and we want to convert it to the atoms of carbon. So both in part A and part B, we're going from grams to atoms. But let me show you the difference between the two, because when you're working out these problems, you need to pay attention for this. So in part A, we've converted the grams of Fe to the atoms of Fe. And in part B, what we need to do is go from the grams of, let's say, glucose to the atoms of carbon. So the difference between part A and part B is that in part A, the substance is not changing. However, in part B, we need to change the substance. So part B requires an extra step relative to part A. So let's begin. Well, first, let's write out a map of what we need to do, or an outline. So we're going to start with the grams of C6H12O6, and then using the molar mass, we're going to convert it to moles. And then once we have the moles, what we could do is convert it to the atoms of glucose. And then once we have that, now we need to change the substance. So we're going to convert glucose into carbon. So the first step, we need to use the molar mass. For the second step, Avogadro's number. For the third step, we need to use the formula that we have here. So let's go ahead and begin. So let's start with what we're given, and that is 356 grams of glucose or fructose. They have the same molecular formula. Now let's convert it to moles. So we need the molar mass. We have 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. So the atomic mass of carbon is 12.01, and for hydrogen it's 1.008, and for oxygen it's 16. So let's go ahead and type this in. So you should get 180.156 grams per mole. So what this means, let me see if I can use less space, is that 1 mole of glucose has a mass of 180.156 grams. Now we could cancel grams and glucose. So now let's use Avogadro's number. So let's use the fact that 1 mole is equal to 6.022 times 10 to the 23. So we could say 1 mole of glucose has 6.022 times 10 to the 23. Now we can't say atoms because C6H12O6, that entire particle, is not an atom, but rather it's a molecule. A molecule is a particle that it's made up of many atoms. So we need to say we have this many molecules of glucose. Let's see if I can fit it in here. I'm running out of space. So now we could cancel the unit moles of glucose. Now the last step, to change the substance, we need to use the chemical formula of glucose. In other problems later in this video, we could use the coefficients of a balanced chemical equation to change the substance. And we'll talk more about that later. But for now, we need to use the formula of glucose, which is C6H12O6. So according to this formula, we could say that 1 molecule of glucose contains 6 atoms of carbon. Do you agree with that? So this is our conversion factor for the last step. So since we have molecules on the top, we need to put it on the bottom. So I could say that 1 molecule of glucose contains 6 atoms of carbon. So now every unit has been canceled except the unit that we want to get, which is atoms of carbon. So now we just got to do the math. So it's going to be 356 divided by 180.156. Take that result and then multiply it by Avogadro's number, and then multiply that by 6. So the final answer that I have is 7.14 times 10 to the 24 atoms of carbon. So that's how you can go from the grams of, let's say, substance A to the atoms of substance B. Now let's move on to part C. What is the mass of a sample in grams that contains 3.5 times 10 to the 24 molecules of SO3? So as always, let's start with what we're given. And let's plan out what we need to do. So we just need to find the mass of the sample. So right now we have molecules of SO3. SO3 is a molecule. It's consistent of, it's made up of many atoms. So once we have molecules, using Avogadro's number, we can convert from molecules to moles, and then using the molar mass, we can go to grams of SO3. Now we don't need to do anything else, because once we have the mass in grams, that's it, we're done. So we don't have to change the substance in this example. So using Avogadro's number, we could say that there's 6.022 times 10 to the 23 molecules of SO3 for every 1 mole of SO3. So we could cancel these units. And now for the last step, which I'm going to rewrite here, we need the molar mass. So we have 1 sulfur atom and 3 oxygen atoms. Sulfur has an atomic mass of 32.06, and for oxygen is just 16. And so you should get 80.06 grams per mole. So what this means is that 1 mole of sulfur trioxide has a mass of 80.06 grams. And so since we had the unit moles of SO3 on the top left, in the third fraction it has to be on the bottom right so that they will cancel. And now let's perform the calculations. So it's going to be this number, 3.5 times 10 to the 24 divided by Avogadro's number. And right now you should have like 5.812, and then we're going to multiply it by 80.06. And so the final answer is 465.3 grams of SO3. And so that's it for this example. Now let's move on to part D, the last part of this problem. Calculate the mass in grams of a sample of silicon tetrafluoride that contains 2.8 times 10 to the 23 atoms of fluorine. I know I marked over it, but that's atoms of fluorine. Feel free to pause the video if you want to try this problem. So we're given the atoms of fluorine, and we need to convert it to molecules of SiF4. So first, let's go from atoms to molecules. And we're going to change the substance. And then we're going to go from molecules to moles using Avogadro's number. And then using the molar mass, we're going to go from moles to grams. So it's helpful if you can write out like an outline of what you need to do with regard to your conversion process. So let's start with what we're given. 2.8 times 10 to the 23 atoms of fluorine. Now, in silicon tetrafluoride, we can say that there's 4 atoms of fluorine for every 1 molecule of silicon tetrafluoride. So this is the conversion factor for the next step. And so I need to put the atoms of fluorine on the bottom. And on top, 1 molecule of SiF4. So I could cancel these units, atoms of fluorine. Now the next conversion factor that we need is this one. We could say that 1 mole of silicon tetrafluoride contains 6.022 times 10 to the 23 molecules of silicon tetrafluoride. So I need to put this part on the bottom. And so I could cancel these units. And on top of the third fraction, I'm going to write 1 mole of silicon tetrafluoride. Now the last step is to convert from moles to grams. And so I need the periodic table for that. So in SiF4, I have 1 silicon atom and 4 fluorine atoms. Silicon has an atomic mass of 28.09, and fluorine has an atomic mass of 19. And so if we add these values, this will give us 104.09 grams per mole. So what we can write in the next fraction is that 1 mole of silicon tetrafluoride has a mass of 104.09 grams. And so now we could cancel the unit moles of SiF4. So to do the math, it's going to be this number divided by 4, which is 7 times 10 to the 22. Take that result, divide it by Avogadro's number. And right now you should have 0.116 and then multiply it by 104.09. So the answer that I have is approximately 12.1 grams of silicon tetrafluoride. And so that's it for this problem. So now you know how to go from grams to atoms and atoms to grams, and at the same time changing the substance from one element into a compound. Number 6. Calculate the mass of 25 carbon atoms in AMU, or atomic mass units, and in grams. So what do you think we need to do in this problem? How can we get the answer? Well, first, let's calculate the answer in AMU. Now, using the periodic table, you'll find that the atomic mass of carbon is this number on the bottom, 12.01. So we can write a conversion factor. We could say that 1 carbon atom has a mass of 12.01 AMU, atomic mass units. So if that's the case, how many atomic mass units are present in 25 carbon atoms? So we're going to set it up as a conversion problem. So we're going to start with what we're given, 25 carbon atoms, and then use this to convert it to AMU. So each carbon atom has a mass of 12.01 AMU. And so we could see the units carbon atoms cancels. And so it's just going to be 25 times 12.01. So the answer for the first part of the problem is 300.25 AMU. Now let's convert this to grams. Another conversion factor that you want to know is that 1 gram is equal to 6.022 times 10 to the 23 atomic mass units. So what we could do is start with 300.25 AMU, and then in the next fraction we could say that 1 gram is equal to this many atomic mass units. And so AMU will cancel, and it's just going to be 300.25 divided by Avogadro's number. And so this will give us this answer, 4.986 times 10 to the negative 22 grams. And so that's how you can convert from atomic mass units to grams. Now, another way in which you could have done this problem, let's say if you just want to go from atoms to grams, you could start with 25 carbon atoms, and then using Avogadro's number, you can convert it to moles. So 1 mole of carbon is equal to 6.022 times 10 to the 23 atoms of carbon. So we could cancel these units. And then we have the molar mass of carbon. 1 mole of carbon has a mass of 12.01 grams. And so this will give us the same answer. And that is 4.986 times 10 to the negative 22 grams of carbon. So as you can see, there's different ways in which you can arrive at the same answer. Number 7. Calculate the percent composition by mass of each element in the compound C6H12O6. So how do we find the mass percent of an element in a compound? Here's the formula that you need to know. So let's say we want to find the percent by mass of the element carbon. What we need to do is take the mass of carbon, this could be just the molar mass of carbon, and divide it by the total mass, or the total molar mass, of the compound, which is C6H12O6. And then we're going to multiply that by 100%. And so that's how you find the mass percent of an element in a compound. It's just the mass of that element divided by the mass of the compound times 100%. So if you want to try this problem, feel free to pause the video and work on it yourself. And then you could play the video again and see if you got the right answer. So let's start with carbon. The molar mass of carbon is 12.01. Now in this compound we have 6 carbon atoms. So we need to multiply the molar mass by 6. Now on the bottom, we're going to put the total molar mass, the total molar mass of the entire compound. And so that's 6 carbon atoms plus 12 hydrogen atoms, where each hydrogen atom has an atomic mass of 1.008. And then we have the 6 oxygen atoms. And then we're going to multiply this whole thing by 100%. So 6 times 12.01, that is 72.06. Now I'm going to type in this whole thing. And let's see what I'm going to get. So the molar mass for the entire compound, that is glucose or fructose, is 180.156. And the units, grams per mole, or you could say atomic mass units. Now remember this number because we're going to use it when calculating the mass percent of hydrogen and of oxygen later in this problem. So 72.06 divided by 180.156 times 100%. So that gives me 39.999%, which I'm going to round it and say it's about 40%. So that's the mass percent of carbon in this compound. Now what about the mass percent of hydrogen? So what we're going to do is take the total mass of hydrogen. So we have 12 hydrogen atoms, each with an atomic mass of 1.008, and then we're going to divide it by the molar mass of the compound, which is 180.156, and then multiply everything by 100%. And so you should get 6.714%. So I'm going to round that and say it's 6.7%. Now the last one is oxygen. So in the compound C6H12O6, there's 6 oxygen atoms, each with an atomic mass of 16. And once again, we're going to divide it by the total molar mass of the compound, which is 180.156, and then multiply it by 100%. The answer that I got is 53.3%. So that is the mass percent of oxygen. Now, notice that if you add up these three numbers, you should get 100%. That has to be the total. Anytime you're calculating the percent by mass of every element in a compound, it should all add up to 100. If it doesn't, that means somewhere along the lines there's a mistake and you need to look for it. So that's it for this problem. Now you know how to calculate the mass percent of an element in a compound. Now here's another question for you. How many grams of carbon are present in a sample of 250 grams of CO2? So how can we convert from the grams of a compound to the grams of an element that is part of that compound? What do you think we need to do here? There's different ways of doing this, but for part A, I'm going to show you one way of doing it. Let's start with what we're given, and that is 250 grams of carbon dioxide. Now here's a question for you. What is the molar mass of carbon, and what is the molar mass of carbon dioxide? The molar mass of carbon, we know, is 12.01 grams per mole. And the molar mass of carbon dioxide is going to be 12.01 plus 2 times 16, which turns out to be 44.01 grams per mole. Now, in 1 mole of carbon dioxide, there are 1 mole of carbon atoms. And so we could say that in this particular example, for every 44.01 grams of carbon dioxide, in it, there's going to be 12.01 grams of carbon, because each of these numbers equal to a mole of their respective substance. And so for this particular example, we could do a gram to gram, excuse me, I just messed up my words there, but we could do a gram to gram conversion. So in this particular example, it's going to be 250 times 12.01 divided by 44.01. And so you should get 68.2, or let's just say 22 grams of carbon. And so that's how you can do a simple gram to gram conversion if you're trying to find the grams of an element within a compound. For other scenarios, when you're dealing with balanced chemical equations, this technique won't work. So just keep that in mind. Now let's try it with part B. How many grams of calcium are present in 890 grams of calcium phosphate? So go ahead and try that problem based on part A. So what is the first thing that you're going to do in this problem? The first thing that I think we need to do is we need to write the chemical formula of calcium phosphate. Calcium is an alkaline earth metal found in group 2A of the periodic table. As a result, it forms a 2+ charge, since it has 2 valence electrons that it can give away. Now, phosphate is one of those polyatomic ions that you should have committed to memory by this point. I hope you did. If you haven't, I recommend that you study that when you get a chance, because these things will keep coming up in the future. Phosphate has a -3 charge, and in order to balance the charges, we need basically 3 calcium ions that will give us a total charge of 6+ or +6, and we need 2 phosphate ions because that will give us a total negative charge of -6. And everything has to be balanced. If it's not balanced, something is wrong. And so the chemical formula is going to be Ca3PO42. Now granted, you could also use the crisscross method if that's what you call it. You could move the 2 here, take the 3, move it there, and you'll get the same formula as well. But the reason why I drew all this stuff is to help you see that the reason why it's written this way is so that the charges are balanced. That's why we need 3 calcium ions and 2 phosphate ions, is so that the positive charges will neutralize the negative charges. So now that we have the chemical formula of calcium phosphate, now we could find the answer to part B. Now the first thing we need to do is calculate the molar mass of calcium phosphate. So we have 3 calcium atoms, 2 phosphorus atoms, and 4 times 2, which is 8, so that's 8 oxygen atoms. Now, the atomic mass of calcium is 40.08, and for phosphorus is 30.97, and for oxygen it's 16. So this is going to give us a total of 310.18 grams per mole. Now let's start with 890 grams of calcium phosphate. And we could say that for every 310.18 grams of calcium phosphate, there's going to be 3 times 40.08 grams of calcium, because there's 3 calcium ions in that compound, each with an atomic mass of 40.08. And so these units will cancel, and it's going to be 890 times 3 times 40.08 divided by 310.18. And so the answer is going to be 345 grams of calcium. Now, for those of you who might feel that this technique, this method is foreign, I'm going to show you another way to do it. And this method might be more familiar to you, so stay tuned. But it's good to understand the different ways in which you can solve a problem. So let's start with what we're given. Now, what I'm going to do is convert it to moles. So 1 mole of calcium phosphate has a mass of, we said it was 310.18 grams, I believe. Now these units cancel. Our next step is to convert from moles of calcium phosphate to moles of calcium. And notice that there's 3 calcium ions in that compound. So we could say that for every 3 moles of calcium, there's 1 mole of calcium phosphate. So we have a 3-to-1 ratio. So now these units cancel. And then the last thing to do is to convert from moles to grams. So based on the molar mass of calcium, 1 mole of calcium has a mass of 40.08 grams. And so now these units cancel. And of course, you're going to get the same answer. Number 9, Part A. So given the percent composition by mass of the elements carbon, hydrogen, and oxygen, how can we determine the empirical formula of the compound? And in Part B, given the molar mass of the compound, how can we determine its molecular formula? So before we begin this problem, let's see the relationship between the molecular formula and the empirical formula. So what do you think is the relationship between these two? So let's say if I have the molecular formula of butane, C4H10. What is the empirical formula? The empirical formula is a formula that contains the lowest ratios, the lowest ratio of whole numbers. There we go. Okay. At first that didn't make sense. So if we divide both numbers by 2, the empirical formula would be C2H5. So you need to find the lowest whole number ratio of the subscripts of the molecular formula. So another example is C6H12O6. Given that, what is the empirical formula for this compound? Well, I could divide 6, 12, and 6 by 6. So if I divide it by 6, I'm going to get C1H2O1, which I can simply write as CH2O. And so this is the empirical formula for C6H12O6. It contains the lowest whole number ratios of the subscripts of the molecular formula. So knowing this, we can now solve this problem. Now, how should we begin? The percents will always add up to 100. And so as a result, what we could do is assume that the compound has a mass of 100 grams. If that's the case, we will have 59.96 grams of carbon, 13.42 grams of hydrogen, and 26.62 grams of oxygen. If we have 100 grams of the compound, which we're going to assume that's the case, just to make life a lot easier. Now, your next step is to convert each of these elements into, or rather, each of the grams of the elements into moles. And so the molar mass of carbon is 12.01. So divide all the masses by their respective molar mass. So this will give us 4.9925 moles of carbon. Now for the next one, the atomic mass of hydrogen is 1.008. So set it up in such a way that the units grams will cancel. So if we take 13.42 and divide it by 1.008, that's going to give us 13.3135 moles of hydrogen. Now let's do the same thing for oxygen. Let's divide it by 16 grams, since that's the molar mass. And so this is going to give you 1.66375 moles of oxygen. Now the next thing that we need to do is divide each of these three numbers by the smallest of those three numbers. And so the smallest is going to be the moles of oxygen. So 4.9925 divided by 1.66375, that's equal to 3. 13.3135 divided by 1.66375, that's going to give us 8. And this is going to be 1. So if all of these numbers are whole numbers, this will be the subscripts for the empirical formula. So it's going to be C3H8O1, or we could simply write it as C3H8O. So that's a simple way in which you can write the empirical formula of a compound. Now, for those of you who want more complicated examples, feel free to check the links in the description section below, and I'm going to post some harder problems, or rather give you links to videos that contain harder problems. So feel free to take a look at that. Now let's move on to part B. So we're given the molar mass of the compound. What is the molecular formula? In order to find the answer, we need to calculate the molar mass of the empirical formula. And so we have 3 carbons, 8 hydrogen atoms, 1 oxygen atom. So this is going to be 3 times 12.01 plus 8 times 1.008 plus 16. And so that comes out to be 60.094. So if this is the molar mass of the empirical formula, and this is the molar mass of the molecular formula, what is the molecular formula? Well, what we need to do is divide the molar mass of the molecular formula by the molar mass of the empirical formula. And so let's go ahead and do that. And so this gives us 3. So what this means is that the molecular formula has 3 times as many atoms as the empirical formula. So to find the molecular formula, what we need to do is take the empirical formula and multiply the subscripts by 3. So it's going to be C9H24O3. And so this is the molar mass of the molecular formula, and 60.094 is the molar mass of the empirical formula. But this is the answer for part B. Now let's work on number 10. An unknown compound contains only carbon, hydrogen, and oxygen. 0.596 grams of this compound generates 1.2093 grams of CO2 and 0.4125 grams of H2O in a combustion reaction in the presence of excess oxygen gas. Determine the empirical formula of the unknown compound. Now this problem is a little bit more difficult than the other ones. So how can we do this? If we could find the grams of carbon and hydrogen and oxygen in the original compound, then we can calculate the moles, and with that, we can determine the empirical formula. So let's focus on calculating the number of grams of each element in this compound. So let's write a combustion reaction. So the compound contains carbon, hydrogen, and oxygen, but we don't know what the subscripts are. So I've labeled X, Y, and Z. And then it's going to react with oxygen gas from the air to produce carbon dioxide and water. Now, what you need to understand is this. All of the carbon in CO2 comes from the compound, and all of the hydrogen atoms in H2O also come from the compound. However, the oxygen atoms do not all originate from the compound. Some of it come from oxygen gas. So in order to calculate the grams of oxygen in the original compound, we need to calculate the grams of carbon and hydrogen, and then using the difference between the total mass of the compound and the masses of carbon and hydrogen, we can calculate how many grams of oxygen is in this compound. And once we have that, then we can calculate the moles of carbon, hydrogen, and oxygen, which will allow us to find the empirical formula. So let's go ahead and begin. Let's start with the grams of carbon dioxide. And let's begin by converting it to moles. So we know that the molar mass of CO2 is 44.01 grams. We've seen it before in this video. So using the periodic table, you can get that answer. Now, there's only one carbon atom for every molecule of CO2. So we could say that there's 1 mole of carbon per 1 mole of CO2. It's in a 1-to-1 ratio. Now that we have the moles of carbon, we can convert it to grams using the molar mass of carbon, which is 12.01. So there's 12.01 grams of carbon for every mole of carbon. So now we could cross out those two units. So 1.2093 divided by 44.01 times 12.01. And so this will give us 0.33 grams of carbon. And so let's save this number for later. Now let's do the same thing with hydrogen. So let's start with 0.4125 grams of H2O. And now let's convert it to moles. So the molar mass of H2O is 18.016 grams. Now, in the next step, we need to convert from moles of water to moles of hydrogen. Now, notice that there's 2 atoms of hydrogen in 1 water molecule. So there's 2 moles of hydrogen for every 1 mole of H2O. It's a 1-to-2 ratio. Now, our next step is to convert from moles to grams using the molar mass. So the molar mass of hydrogen is 1.008. So there's 1.008 grams of hydrogen per 1 mole of hydrogen based on the periodic table. And so it's going to be 0.4125 divided by 18.016 times 2 times 1.008. And you should get 0.04616 grams of hydrogen. So now we need to calculate the grams of oxygen. So what we need to understand is this. The total mass of the compound is going to equal the mass of carbon plus the mass of hydrogen plus the mass of oxygen. So if we take the total mass and subtract it by the mass of carbon and the mass of hydrogen, it should give us the mass of oxygen. The total mass of the compound is 0.596 grams, and the mass of carbon is 0.33, and the mass of hydrogen is 0.04616. So therefore, the mass of oxygen is going to be 0.21984 grams. Now that we have the mass of every element, let's calculate the moles of each element. So let's start with the grams of carbon, and let's convert it to moles. So the molar mass of carbon is 12.01 grams. So we have 0.33 divided by 12.01, and that's going to give us 0.02748 moles of carbon. Now let's do the same thing with hydrogen. So the molar mass for hydrogen is 1.008 grams. So 0.04616 divided by 1.008, that's going to give us 0.04579. And so that's the moles of hydrogen. Now let's do the same thing for oxygen. So the molar mass of oxygen is 16. And so this is going to give us 0.01374. Now what we need to do is divide each of these numbers by the smallest of these three numbers. And the smallest is the moles of oxygen. So this is going to give us 1. If we divide the moles of hydrogen by 0.01374, that's going to give us 3.33. And if we do the same thing with the moles of carbon, that's going to give us 2. So right now, this indicates that the formula is C2H3.33O1. So I'm going to write that here, C2H3.33O1. Now, of course, we're going to have to modify that a bit, but let's just erase this first. So we need to multiply the subscripts 2, 3.33, and 1 by something in order that all the three numbers are whole numbers. What shall we multiply it by? Now, with this example, you can probably see what it is. But for other examples where it's not easily detectable, it helps to be familiar with fractions. 1 over 2 is 0.5. So if this was 3.5, I would multiply it by 2. 1 over 3 is 0.33. Since we have 0.33, I need to multiply everything by 3. But let's say if I had 0.25, I would multiply it by 4. If I had 0.2, I would multiply it by 5. If I had, let's say, 0.16 repeated, I would multiply it by 6. And so by understanding fractions and the decimals that are related to them, that can tell you what you should multiply the subscripts by. So in this case, we're going to multiply each subscript by 3. So 2 times 3 is 6. 3.33 times 3 is basically 9.99, which can be rounded to 10, and 1 times 3 is 3. So the empirical formula is going to be C6H10O3. And so that's how you could find the empirical formula using combustion analysis. Number 11. Octane reacts in air to produce carbon dioxide and water. How many moles of oxygen gas is needed to react with 14 moles of octane? So this is basically a reaction stoichiometry problem. And the first thing we need to do is write a balanced chemical equation. So we have octane, C8H18, which reacts with oxygen gas, which is in the air, and it's going to produce carbon dioxide and water. So let's write the elements that we have on the left side and on the right side. So as of now, we have 8 carbon atoms on the left 18 hydrogen atoms and 2 oxygen atoms. On the right side, we only have 1 carbon atom, 2 hydrogen atoms, and 3 oxygen atoms. 2 plus 1 is 3. So let's begin by balancing the carbon atoms. So what I'm going to do is put an 8 in front of CO2. And so this number becomes an 8. So the number of carbon atoms are equal. Next, I'm going to balance the number of hydrogen atoms. I'm going to put a 9 in front of H2O because 9 times 2 is 18. Now, the next thing I need to do is balance the oxygen atoms. Right now, on the right side, I have 8 times 2, so that's 16 oxygen atoms in CO2, and 9 times 1, so that's 9. 16 plus 9 gives me 25. Now, what I need to do is I need to put 25 over 2 in front of O2, because 25 over 2 times 2 will give me 25 oxygen atoms. And so it's balanced, but I don't want to have any fractions here. So what I'm going to do now is I'm going to double everything. So this one, I'm going to change it to a 2. And 25 over 2, if you multiply that by 2, the 2 on the bottom disappears, and you just get 25. 8 times 2 is 16, and 9 times 2 is 18. So now, if we count the number of carbon atoms on the left side, we can see that it's 2 times 8, which is 16. On the right side, it's 16 times 1. So that's good. So these two are now equal. Now let's consider the number of hydrogen atoms. Here it's 2 times 18, which is 36. And here's the same thing, 18 times 2, that's also 36. So those atoms are balanced. Now lastly, we have the oxygen atoms. 25 times 2 is 50. And on the right side, we have 16 times 2, which is 32 plus 18. So that's also 50. And so now the equation is balanced. So now that we have a balanced chemical equation, we can use that to answer the other parts in this video. So let's begin with part A. How many moles of oxygen gas is needed to react with 14 moles of octane? So what we need to do in part A is convert from the moles of substance A to the moles of substance B. So we're not changing the unit, all we need to do is change the substance. In this case, substance A is octane and substance B is O2, because that's what we're looking for. We're looking for the moles of oxygen gas. So we need to perform a mole-to-mole conversion. So let's start with what we're given, and that is 14 moles of octane. Now, to convert from one substance to another, we need to use the molar ratio. So we're going from octane to oxygen gas. And notice the coefficients, 2 and 25. So what that means is that 2 moles of octane are needed to react completely with 25 moles of O2. And so that's what it means. And so we're going to use this as our conversion factor. This is what we need to go from moles of octane to moles of O2. So on the bottom, we're going to write 2 moles of octane, and on the top of the fraction, we're going to write 25 moles of O2. And so this is known as a molar ratio. So now the unit moles of octane will cancel. And so the answer is going to be 14 divided by 2, which is 7, and 7 times 25. Well, if you have 7 quarters, that's $1.75. So 7 times 25 is 175. So what this means is that 14 moles of octane will react completely with 175 moles of oxygen gas, according to this balanced chemical equation. Now, part B. How many grams of octane is needed to produce 8.5 moles of CO2? So this time, we're given the moles of substance A, and we need to convert it to the grams of substance B. In this case, A is CO2, B is octane. So what we need to do in this example is we need to convert from moles of A to moles of B. Whenever you want to change the substance, you need to use the balanced chemical equation. And so you need to use the molar ratio. Next, once we have the moles of B, we can use the molar mass to go from the moles of B to the grams of B. And so we're going to change the unit from moles to grams. So this is going to be a two-step process. So let's begin with 8.5 moles of CO2. Always start with what you're given. Now we need to change the substance from CO2 to octane. And so the molar ratio is 16 to 2. So what we can say is that for every 16 moles of CO2 that is produced in this reaction, 2 moles of octane is consumed. So now we could cancel these units. Our next step is to convert from moles to grams. So we need the molar mass of octane. So we have 8 carbons and 18 hydrogen atoms. So this is going to be 8 times 12.01 plus 18 times 1.008. And so this is going to give us 114.224 grams per mole. And so we could say that for every mole of octane, there's 114.224 grams of octane. And so now we could cancel these units. So once you have your desired unit, you can now basically do the calculation. So it's 8.5 times 2 divided by 16 times 114.224. And so you should get 121.363 grams of octane. So that's it for this problem. Now let's move on to part C. How many moles of H2O will be produced if 75 grams of octane reacts completely with excess oxygen? So this time we're given the grams of substance A, and we need to convert it to the moles of substance B. So A is octane, B is water. So what we're going to do is we're going to start with the grams of octane, and then we're going to convert it to the moles of octane using the molar mass. And then once we have that, we're going to use the molar ratio to go from octane to H2O. And so just like the last problem, this is a two-step problem just in reverse. So let's start with what we're given, 75 grams of octane. And let's begin by converting it to moles. And so the molar mass of octane is 114.224 grams per mole. Now our next step is to use the molar ratio. So the molar ratio between octane and water is 2 to 18. So we could say that for every 2 moles of octane that reacts, 18 moles of water will be produced. So let's do the math. It's going to be 75 divided by 114.224 times 18 divided by 2, or just times 9. And so I got 5.909 moles of H2O. And so that's it for part C. Now, let's move on to part D. What is the maximum amount of CO2 in grams that can be produced if 150 grams of octane reacts completely with excess oxygen? Now, anytime you wish to calculate the maximum amount of product that can be produced, it could be in moles, but usually it's in grams. That represents what is known as the theoretical yield. That's the most you can get in a reaction if it's 100% efficient. Now, granted, some reactions will not be 100% efficient. Actually, almost all reactions are never 100% efficient. And so there's something called percent yield, which is actual yield over theoretical yield times 100%. But we're going to talk about that in another problem. But for now, note that the theoretical yield is the maximum amount of product that you can get in a chemical reaction. Let's talk about what we need to do in order to get the answer for part D. So we're given the grams of octane, so let's say that's the grams of substance A, and our goal is to calculate the grams of CO2, or the grams of substance B. Now, in order to do this, we need to start with the grams of substance A and convert it to the moles of substance A using the molar mass of substance A. Next, using the molar ratio, we need to change the substance from A to B. And then once we do that, we can use the molar mass of B to go from the moles of B to the grams of B. So that's the process that we need to follow in this example. So let's start with the mass of what we're given, octane. And let's convert it to moles. So we know that 1 mole of octane has a mass of 114.224 grams. And make sure the units cancel. So just double check that. Now we need to use the molar ratio. So we're going from octane to CO2. So it's 2 to 16. So for every 2 moles of octane that reacts in a reaction, 16 moles of CO2 will be produced. And so now we could cancel these units. Now the last step is to convert from moles to grams. So we already know the molar mass of CO2. We've seen it many times. It's 44.01 grams per mole. So now we can get rid of these units. And let's get the answer. So it's going to be 150 divided by 114.224 times 16 divided by 2 times 44.01. And so I got 462.35 grams of carbon dioxide. So this is the theoretical yield of CO2. That is the maximum amount of CO2 that we can possibly get in this reaction given 150 grams of octane and assuming the reaction is 100% efficient. Number 12. Carbon monoxide reacts with oxygen gas to produce carbon dioxide. Identify the limiting reactant if 8 moles of carbon monoxide is mixed with 5 moles of oxygen gas. Well, let's begin by writing a balanced chemical equation. So we have carbon monoxide plus oxygen reacts to produce carbon dioxide. And just to balance it quickly, what we need to do is put a 2 in front of CO and CO2. So we have 2 carbon atoms on both sides. And right now we have a total of 4 oxygen atoms on both sides. So here we have 2 plus 2, that's 4. and 2 times 2 is 4 as well. So if we mix 8 moles of carbon monoxide with 5 moles of O2, which one is going to be the limiting reactant? Now, the limiting reactant is simply the reactant that runs out first. As the reaction progresses, the amount of carbon monoxide and oxygen will eventually go to zero. And they don't have to reach zero at the same time. One of these reactants will hit zero first. Is it going to be carbon monoxide or oxygen gas? Now, you might be inclined to think that it's going to be O2 because we have less of it. And that would make sense. However, more is involved. The simplest way to identify the limiting reactant is to see which reactant has the lowest mole per coefficient ratio. So what you need to do is take the number of moles and divide it by the coefficient of the balanced reaction. So 8 divided by 2 is 4, 5 divided by 1 is 5. So notice that CO has the lowest mole per coefficient ratio. Thus, carbon monoxide will run out first. So that is the simplest way in which you could determine which one is going to run out first. So carbon monoxide is known as the limiting reactant. Oxygen is known as the excess reactant. Now, another way to help understand this concept visually or even numerically is to remember that for every 1 mole of oxygen gas that reacts, 2 moles of carbon monoxide will react. So carbon monoxide is being depleted faster than O2. And so let's see what happens over time. So right now we started with 5 moles of O2. When 1 mole of O2 reacts, we're going to have 4 moles left over. Now remember, it's a 1 to 2 ratio. So after 1 mole of O2 reacts, 2 moles of CO will react. So 8 minus 2 is 6. Now after another mole of O2 reacts, so it's going to go from 4 to 3, another 2 moles of CO will react. So it's going to go from 6 to 4. So notice that O2 is decreasing by 1 every turn, whereas CO is decreasing by 2 because it's a 1 to 2 ratio. And so we're going to see which one is going to hit 0. So by the time this is 2, this is going to decrease to 2. By the time this is 1, this is going to hit 0. So notice that CO runs out first because it's decreasing at a faster rate. So CO is the limiting reactant. And when its reaction is completed, we're going to have 1 mole of the excess reactant left over. So this is why it helps to find the moles per coefficient ratio. Whichever reactant has the lowest mole per coefficient ratio, that's the one that's going to run out first. Now, let's move on to part B. So this time, we're going to have 16 grams of carbon monoxide and 12 grams of oxygen gas. So if we're given the grams of each reactant, how can we identify the limiting reactant? The best thing to do is to calculate the moles of each respective reactant. So let's start with 16 grams of CO. Now the molar mass of carbon monoxide is going to be 12.01 plus 16, which is 28.01. And so we could cancel these units. 16 divided by 28.01 is, I'm going to write it here, 0.5712. So that's how many moles of CO that we have in this reaction. Now let's do the same thing for O2. The molar mass of O2 is 16 times 2, which is 32. And so 12 divided by 32 is 0.375. So now that we have the moles of each reactant, we can now calculate the mole per coefficient ratio. So we have a 2 in front of CO, therefore we need to divide this number by 2. So 0.5712 divided by 2, so that's going to be 0.2856. And if we divide this by 1, we're just going to get 0.375. So once again, CO has the lowest mole per coefficient ratio. Therefore, CO is the limiting reactant, O2 is the excess reactant. Now, what you want to take from this problem is that the limiting reactant doesn't have to be the one with the lower number of grams. That's not always the case, nor is it the one with the lowest number of moles, but rather, the limiting reactant is the one with the lowest mole per coefficient ratio. As long as you take the moles and divide it by the respective coefficient for that substance in the balanced chemical equation, then the lowest number of this value would give you the limiting reactant. So make sure you understand that for future problems. Now let's move on to this problem. 30 grams of pentane is mixed with 85 grams of oxygen gas. Identify the limiting reactant. So first, let's write a balanced chemical equation. Pentane is C5H12. So we're going to react that with oxygen gas, and that's going to produce carbon dioxide and water. So let's balance the chemical equation. When balancing combustion reactions, it helps to balance the carbon atoms first. We have 5 carbon atoms on the left side, and so let's put a 5 in front of CO2. Now we have 12 hydrogen atoms on the left, so we need to put a 6 in front of water, because 6 times 2 is 12. Next, count the total number of oxygen atoms. So in 5 molecules of CO2, we have 10 oxygen atoms, and in 6 molecules of water, we have 6. 10 plus 6 is 18. I mean, not 18, that's 16. Definitely not 18. And so 16 divided by 2 is 8. So now, the chemical reaction is balanced. Now let's identify the limiting reactant. So we have 30 grams of pentane mixed with 85 grams of O2. So let's calculate the moles of each substance. Now we need the molar mass of pentane. And so that's going to be 5 times 12.01 plus 12 times 1.008. And so the molar mass of pentane is 72.146. So now let's divide these two numbers. 30 divided by 72.146 comes out to be 0.4158 moles. Now let's do the same with O2. So we have 85 grams of O2, and the molar mass is still 32. So 85 divided by 32, that's 2.656 moles. So now let's calculate the mole per coefficient ratio. So this number, we just need to divide it by its coefficient, which is 1. So we're just going to get 0.4158. This number, we need to divide it by 8. And so that's going to be 0.332. So O2 has the lowest mole per coefficient ratio, which means that it is the limiting reactant, and pentane is the excess reactant. Now let's move on to part B. Calculate the theoretical yield of CO2 in grams. So the theoretical yield is the maximum amount of CO2 that can be produced in this reaction. To calculate it, we need to convert the grams of the limiting reactant to the grams of CO2. Now, there's a way in which we can get the answer for part B and A at the same time without doing what we did in part A, without calculating the mole per coefficient ratio. And to get the answer, it's important to understand that the limited reactant will give us a lower theoretical yield of CO2. The excess reactant will give us a higher theoretical yield of CO2. So what you need to do is take the mass of the limited reactant and convert it to the grams of CO2. And then separately, take the mass of the excess reactant, convert it to the grams of CO2. Whichever of these two reactants give you a lower theoretical yield, that's going to be the limited reactant. And automatically, the other one is the excess reactant. So that's how you can do part A and B at the same time without calculating the mole per coefficient ratio. So let's go ahead and do that in this example. So let's start with the 85 grams of the limiting reactant, O2. Now, we need to do a gram to gram conversion. So we're going to start with the grams of substance A, convert it to the moles of substance A, using the molar mass, and then using the molar ratio. We're going to change from substance A to B, and then we're going to use the molar mass of substance B to convert it to the grams of B. So B is CO2, A is O2 in this example. So we know that the molar mass of O2 is 32 grams per 1 mole. Now don't forget to set it up in such a way that the unit grams cancel. Now let's use the molar ratio between O2 and CO2. So it's 8 to 5. For every 8 moles of O2 that reacts, 5 moles of CO2 will be produced. Now finally, what we need to do is convert moles of CO2 into grams using the molar mass, which is 44.01 grams per mole. So the unit moles of O2 cancels, and the unit moles of CO2 will cancel as well. So it's going to be 85 divided by 32 times 5 divided by 8 times 44.01. And so I got 73.06 grams of carbon dioxide. So what this means is that if all of the 85 grams of O2, if all of it reacts, the maximum amount of CO2 that can be produced is 73.06 grams. Now let's start with 30 grams of pentane, C5H12. Now the molar mass of pentane is going to be 72.146 grams. Now, we need to use the molar ratio to convert it from moles of pentane to moles of CO2. So we have a 1 to 5 ratio. So for every 5 moles of CO2 that's produced, 1 mole of C5H12 will be used up. Now the last step is going to be the same. The molar mass of CO2 will not change. I'm trying to conserve as much space as possible. So now it's going to be 30 divided by 72.146 times 5 times 44.01. And so notice that we get a higher amount, 91.50 grams of carbon dioxide. So as you can see, once you do it this way, automatically you know which one is the limiting reactant. The limiting reactant is the reactant that generated a lower theoretical yield. The excess reactant produces a higher theoretical yield. So O2 was the reactant that gave us this number. So thus O2 is the limiting reactant. And the other one, pentane, is the excess reactant in this example. Now the actual theoretical yield is going to be the lower of these two values. The theoretical yield is based on the limiting reactant, because once the limiting reactant is completely consumed, the reaction stops. If one of these guys disappears, there is going to be no reaction. They need each other to react. So once the quantity of O2 hits 0, the reaction stops. So the answer to part B, the theoretical yield of CO2 in grams, is 73.06 grams of CO2. So that is the maximum amount of carbon dioxide that can be produced in this reaction. Now let's move on to part C. If 56 grams of CO2 is collected in the reaction, what is the percent yield? Percent yield is equal to the actual yield divided by the theoretical yield times 100%. So in this example, the actual yield is 56 grams of carbon dioxide because that's the amount that was actually collected. The theoretical yield, the most that we can get, experimentally speaking, is 73.06 grams. And so if we divide 56 by 73.06 and then multiply that by 100%, we're going to get 76.65%. And so that is the percent yield of this reaction. This tells you how efficient the reaction is. Now let's illustrate the relationship between the actual yield, theoretical yield, and percent yield using numbers. So let's say that the theoretical yield of CO2 is 200 grams. That is the maximum amount of CO2 that we can possibly get in this reaction. This is the ideal amount, the most we can get. And let's say if the percent yield is 80%. How many grams of CO2 are we expecting to collect in this reaction if it's 80% efficient? Now, if it was 100% efficient, then we would actually collect the most that we can get, 200 grams. But since it's 80% efficient, we're going to get 80% of 200. And so that's going to be 160. So basically you take 200 and multiply by 0.80. So this number here, the maximum that we can get, this is known as the theoretical yield. And the amount that we actually got in the experiment, that is the actual yield. The efficiency, which is this number, that is the percent yield. So knowing that, let's answer the last part of this question. How much CO2 is expected to be collected if the reaction is 90% efficient? So we have the theoretical yield. It's 73.06 grams of CO2. Now, if the reaction is 90% efficient, that is, if the percent yield is 90%, what is the actual yield? So all it is 73.06 times 0.90. And so you should get 65.754 grams. So if the process is 90% efficient, this is going to be the actual yield. Now this is going to be the last problem of this video. And I just want to say that if you want more practice problems on any of these topics, check out the links in the description section of this video. And I'm going to post more links to other videos with more problems. And also, whatever you do, don't forget to subscribe to this channel. If you do, I will greatly appreciate it. And don't forget to click on the notification bell if you decide to subscribe, so you can receive updates on any new videos I'm going to post in the future. Now let's get back to this problem. So here we have SO2 being mixed with O2. And one thing I forgot to do is write the product of the reaction. So let me give it to you before you start working on this problem. So here's the reaction between SO2 and O2. So feel free to pause the video and work on the rest of this problem at this point. Now the first thing we need to do is balance the chemical equation. Right now the sulfur atoms are balanced, but not the oxygen atoms. So what we're going to have to do is increase the number of sulfur atoms. If we do it like this, everything will be balanced. So we have 2 sulfur atoms on both sides. Here we have 4 oxygen atoms plus 2, and 2 times 3 is 6. And so we have a total of 6 oxygen atoms on both sides at this point. Now for those of you who want more practice problems on balancing equations, just do a YouTube search and type in organic chemistry tutor. I do have some other tutorials on balancing chemical equations. Now let's begin by calculating, or rather identifying, the limiting reactant. So let's calculate the moles of each substance. Let's start with the 45 grams of SO2. The molar mass of SO2 is 32.06 plus 2 times 16, and so that's going to be 64.06 grams. So 45 divided by 64.06, that's going to give us 0.702. I'm going to add another number, 0.7025 moles of SO2. Now let's take the 72 grams of O2 and let's convert it to moles. So the molar mass is still the same. 72 divided by 32, that's going to give us 2.25 moles of O2. Now to identify the limiting reactant, we need to calculate the mole per coefficient ratio for each reactant. So this one, we're going to divide it by 2. 0.7025 divided by 2, that's going to be 0.35125. This one, we need to divide it by 1, so it's not going to change. So as we can see, SO2 has the lowest mole per coefficient ratio. So this is going to be the limiting reactant, and O2 is the excess reactant. Now, part B. Calculate the amount of excess reactant that will be left over after the reaction is complete. How can we do that? How can we find out how much excess reactant will be left over? Well, in order for us to do that, we need to find out how much will be consumed in the reaction. Now, we know that all of the 45 grams of SO2 will be consumed because it's the limiting reactant. And so if we take this amount and convert it to the grams of O2, it's going to tell us how much O2 will be consumed in the reaction as this depletes to 0. And so if we take that amount and subtract it from 72 grams, that's going to give us the amount of O2 left over. So make sure you understand that. So when answering a question like this, when you're trying to find the amount of excess reactant that is left over, start with the grams of the limiting reactant and convert it to the grams of the excess reactant. So let's take the grams of SO2 and let's convert it to moles. The molar mass of SO2, we said it's 64.06. Now let's use the molar ratio between SO2 and O2. So for every 2 moles of SO2 that reacts, 1 mole of O2 reacts with it. Now our next step is to convert moles of O2 into grams using the molar mass of O2, which is 32 grams per mole. So this is going to be 45 divided by 64.06 times, or rather divided by 2, and then times 32. So this is 11.24 if you decide to round it. So this is the amount of the excess reactant that is actually consumed in the reaction. So let's think about this. We started with 72 grams of O2, and only 11.24 grams of O2 was used up. How much is left over? So it's going to be 72 minus 11.24, which is 60.76 grams. So that is the amount of O2 that is actually left over in the reaction. That's how you find it. And that's basically it for this video. Hopefully the information presented here will be enough for you to do well on your upcoming stoichiometry exam. And whatever you do, don't forget to subscribe to this channel if you really like this video. Thanks again for watching.